Hi, we are Team Quantum Robotics, and we're proud to present our 2025 System Acceptance Review for the University Rover Challenge.
We learned a lot from last year's competition. That's why we focus on improve and updating our rover core system. And also, we implemented a training and onboarding program for newer members.
We have improved on our reliable simplified rocker suspension by replacing T-slot profile rockers with round tubing for reduced weight and better torsional rigidity. Additionally, we have improved on our 3D printed wheels by changing our spoke structure with 3D printed plastic and aluminum rims. These upgrades improve overall maneuvering over every terrain featured at the MDRS. We increased also aluminum PETG sandwich composite usage on key components that need high strength and low mass, like wheel hubs, suspension structures, and gearboxes. Furthermore, we have developed an all-new chassis, increasing internal volume by 30% while reducing 50% of the mass. In addition, we added hard points in every surface in order to ease and speed up the module mating process, as well as enable a variety of configurations and customization.
For electronics, we used two high-discharge LiPo batteries in order to supply the necessary power to all brushless motors.
We also redesigned the power distribution center to make connections to the various electronic components simplifier and faster. Also, the maximum output voltage of the power distribution center was adjusted to 12 volts instead of the previous year's 24, since the same motors will not longer be used for the arm. As for the arm, to improve efficiency, a printed circuit board was built to control its position at all times by means of absolute encoders. The rover has a main breaker which can cut power to all motors in case of emergency.
We have continued working with two omnidirectional antennas using the 900 MHz frequency, taking advantage of its range and the performance of the MIMO system antennas. In our tests, we managed to establish communication from up to 800 meters away. Furthermore, we are going to implement a new signal repeater for longer distances and to avoid signal interruptions caused by the obstacles between the base station and the rover.
We have three computers in our base station, which communicate through the ROS2 framework and WebSockets with the rover's Jetson Orin Nano. With this, we can control the rover's movements and visualize inputs from cameras and sensors.
This year's autonomous navigation solution is built upon three main components.
GPS coordinate mapping, where we turn GPS feedback into an XY plane for easier calculations, efficient path planning, and navigation. The second component we have is the obstacle evasion, where we get feedback from the Z2I camera, the LiDARs, and the IMU, and we improve this feedback of the sensors with a Kalman filter to assess the risk of any given path while traversing the terrain. And the object detection and search routine, we make a systematic search over a 20-meter radius, and during this process we actively scan for nearby obstacles and for the given target, either the AirTag, the hammer, or the bottle.
We developed a 5 degree of freedom robotic arm, actuated with worm gear reductors to allow high torque, low backlash, and non-backdrivable joints to improve precision and precision control. Our end effector got a full redesign, switching from an angular claw to a worm gear actuated linear gripper. This kind of effector allows us for precise movements, crucial for autonomous typing tasks, as well as the rest of the fine movement tasks. Each of the arm's joints work with a CAN protocol, providing closed-loop feedback for precise control. We use forward and reverse kinematics for our robotic arm, which can be controlled by a graphic user interface combined with a teleoperated control that allows us to manipulate the end stool effector into specific positions. As well, a 2D visualizer is utilized to verify the position of the joint at all times. This helps us to have a practical and efficient performance during all manipulation tasks.
The astrobiology and geology team will be carrying out the light detection analysis using colorimetric reagents to determine biomarkers that will tell us about the presence or absence of life or extinct life, such as proteins, lipids, and carbohydrates.
Analysis on site will also be supported by the implementation of a microscope. On the other hand, the analysis on board will be assisted through an interface, allowing the team to know the characteristic of the sites chosen. To accomplish the geology task, we used two telescope screws located on the underside of the rover, one equipped with a fitted auger drill and the other with a humidity and temperature sensor. The drill probe interacts with a load cell module that uncouples the auger in order to weigh the surface sample. We also developed a rock database that provides detailed and useful information about the site's rock samples. Additionally, for the geology task, we implemented a program that identifies rocks strata in images using 3S holding, color palette, and texture analysis in the site's photographs, enabling us to analyze and explain the site's water history.